If you recall from the end of Friday's lecture, we talked a lot about chemical safety and storage for flammable liquids. And so for any category 1 flammable liquid, we talked about how they had to be bonded to each other and grounded to the earth as part of the general safety with regard to um, uh, dissipation of charge and static electricity. We talked about safety cans and the different kinds of measures inside of the cans that allow that flap to open to effectively burp the can in the event that the pressure inside became too great. And we talked about flammable cabinets and how flammable cabinets are made of flame retardant, relatively fireproof materials, and that they do have these vents at the top to allow for excess pressure to escape relatively easily without causing the entire cabinet to explode. Now, when it comes to portable tanks, um, any kind of portable tank is, by definition, something that is a closed container that is not intended for a fixed installation. So we're never going to bolt this to the ground or keep it in one location permanently. It's got to be something that is movable and can possess a capacity of up to 60 gallons. And portable tanks require one or more devices for emergency venting under fire conditions. And so you can see those kinds of things. They usually have relief valves on them somewhere, kind of long stick-like protrusions from them that act as pressure relief valves in the event that something were to go wrong and they were to gain excess pressure in some kind of way. Now, when things do go bad, the most common kind of incident that is present is something called a BLEVE. And what ultimately is happening in a BLEVE is this. You've got a fire going on, and that fire is starting to kind of collapse upon and engulf the flammable liquid container, and something happens that ultimately causes essentially an explosion. So BLEVE is short for boiling liquid expanding vapor explosion. Basically, what that means is as the heat is taking over this tank, the liquid that is on the inside is going to start to rise in temperature. Now, as you know, a rise in temperature is going to immediately cause a rise in vapor pressure to the point where it's not going to take long, since the tank is completely enclosed. It's not going to take long for that pressure to reach the atmospheric pressure and start boiling the liquid inside. As that liquid is boiling on the inside, the pressure starts to increase and it starts to increase and it starts to increase until essentially it breaks through the pressure allowance of the tank and ruptures the tank. And when the tank ruptures, all of that boiling liquid is released simultaneously. And since it is flammable and it is surrounded by flames, we get a gigantic fireball, a huge explosion, lots of damage, lots of heat, and potentially lots of loss of life, depending if things are around it. This is an example of kind of an extreme case of a BLEVE. Now, way back in the background there, let me draw a little circle for you. This is the source of the BLEVE. That is a train. Um, and the train in this case was carrying some flammable liquids in a tank car. The train had an accident of some sort, and started to catch on fire. And the flammable tank cars that were behind it, one of them ended up rupturing and causing this massive, massive, massive fireball. So that's kind of the thing that ultimately we are trying to avoid in any case when we are looking at um, a potential fire around flammable materials is if we can get the material safely cartoned away. Obviously we're going to try to do that. We're going to try to fight the fire before it gets to that point where it starts to impinge on the vessels themselves. But at some point in time, and this is well documented, at some point in time, there is kind of a break all condition scenario where basically firefighting crews and anybody else go, okay, this is beyond salvage. Let's get everybody out of here so that nobody gets hurt by this. And they end up having to cordon off an area about a mile of radius from the zone to make sure that the blast does not end up hurting anybody. And then they themselves have to stay about half a mile away until it occurs. And then once it occurs, they can kind of come back in and try to deal with um, the flame and making sure it doesn't spread too much. But um, when you get to that point where a BLEVE is likely, the primary risk is people dying, and so they really work hard to make sure that everybody gets cleared out of the area so that nobody gets hurt by it. So a little bit more about BLEVEs. When flames start to move into that vapor space, so we're no longer just boiling the liquid, we now have all of that vapor on top of it, and the flames are starting to kind of eat through the material. We're going to get flame into that vapor space. We know that a BLEVE is eventually going to occur. And like I said, that's kind of our kill all, break all kind of scenario. When this starts to occur, we make sure that everybody is out of the way. And so again, depending on the size of the tank, evacuation distances can range up to about half a mile for emergency responders and about a mile for general public. This picture, as evidenced by how small that train is in the background there, gives you an idea of how far away that person was when they took this particular picture. That they were a good bit away for obvious reasons. As I mentioned before, as those flames start to surround that tank, again, the increase of temperature is going to be what is going to cause the liquid to first start evaporating faster, increasing its vapor pressure, and then eventually starting to boil off the liquid itself. Now, this is an important note. The pressure relief valves inside of the tanks should respond to these increases in pressure, at least initially. But we cannot rely on them solely. So if the flame impingement on the liquid space and it's just causing more boiling, more pressure, if we just kind of let that go and we don't try to intervene in any kind of way, then a BLEVE could still occur. Yeah, BLEVE really only occurs when that flame gets into the vapor space, because now the vapor is what is ultimately flammable. But if we have it on the underside, if we have it on the liquid side, the potential does exist for one if that pressure release isn't monitored well. And so that there is the end of our chapter 3 discussion. Any questions about flammable liquids before we sign off from chapter 3 and move on into chapter 4? All right, so in chapter 4, chapters 4 and 5, honestly speaking, are probably the most chemistry heavy, chemistry intensive chapters of the entire course and in the entire book. These are really the last 2 chapters that we're going to really get into deep chemistry. The rest of them are going to be mostly focused on applying these principles of chemistry to other areas, to other kinds of hazardous materials. So we're going to start our discussion of chapter 4 with probably the most quintessential kind of discussion of chemistry, and it's related to that picture that's behind me, the periodic table of elements. Now, if you've ever looked closely at the periodic table of elements, what you'll notice is that it is kind of a weird looking shaped table. It's not arranged in traditional rows and columns. It's not a matrix of sorts. It's kind of disjointed in some kinds of ways. But the reason why it is arranged the way that it is to do a couple of really key things. First of all, if I look at any column in the periodic table, whether it be the metals over here on the left or the nonmetals over here on the right, you'll find that inside any one single column, you have elements that have very similar properties to each other. And we call this arrangement the periodic law. The periodic law states that when we arrange the elements in the periodic table appropriately, they should line up so that individual elements in a given column have similar chemical and physical properties. And what this allows us to do is this allows us to start to characterize and classify groups of elements by their common characteristics instead of individually as their own kind of entities. Because as you can imagine, with 118 elements on the periodic table, if we wanted to describe each of them individually, that would be 118 individual descriptions. Whereas I can look at those 6 elements in the first column, notwithstanding hydrogen, and go, okay, in that group, we expect this property and this property and this property and this property. So the periodic table has a dualistic kind of arrangement. Elements in each column, so again, column being vertical groups, these are called families. So a vertical column can be referred to as a group or as a family. elements in the same row are said to belong to a given period. So a horizontal row is known as a period. And generally speaking, periods describe the number of energy levels that have electrons in them for a given element. So if I look at that third row of the periodic table, every single one of those elements has electrons in the first energy level, the second energy level, and the third energy level. If I look at the fifth period, all of those elements have electrons in the first energy level, the second energy level, the third energy level, the fourth energy level, and the fifth energy level. So we can start to kind of build out a case for, okay, this is what makes these vertical columns kind of click. This is what makes these horizontal rows kind of click. And when I put those two together, I can get a more complete picture of what's going on inside of that atom. This is a completed example of the periodic table of elements. Every element has a couple of key features and attributes that are worth mentioning. As you can see, all of the groups have been appropriately labeled, starting with 1 up here at the top, and all the way to 18 over here in that last column with helium. All of the rows have been labeled accordingly as well. There are 7 periods in the periodic table, and that means that there are 7 energy levels that are capable of holding electrons in a given atom. However, most elements do not use most of the energy levels. In fact, only when we get to period number 7 here do we see the 7th energy level even in use. If I start to put the two ideas together, so if I draw crosshairs between the group and the period, I can arrive at an individual atom like sulfur here. And so sulfur is in group 16, period 3. Other information we can get from the periodic table, aside from, kind of coordinate information, we saw a little bit of this when we did chapter 2. We're going to talk a little bit more about it here. We get here in green, this is the atomic number for a given element. And remember that the atomic number is the number of protons in an element's nucleus. In blue here, we can get the elemental symbol. For a given element. Which is a 1 to 2 letter abbreviation for each element. And then the last thing that we can get from the periodic table is this information here at the bottom in brown. This is the atomic mass of the element. And the atomic mass is the average mass of an atom for the element in AMU, atomic mass units. Now, this is not to be confused with the mass number. Mass number we'll talk more about in chapter 16. The mass number is the number of protons and neutrons in the nucleus. So that's not a piece of information that we can get from the periodic table. We can only get a mass number from an individual isotope's description. But there are lots of other things that we can get from the periodic table itself. So this is kind of general information about any individual element. There's also some other information that we can acquire as well. So things like there is a defining line between metals, nonmetals, and metalloids on the periodic table. So I can look at the periodic table and distinguish, okay, this is the area where it is metal, this is the area where it is nonmetal, the area in between is where there are metalloids. And as I mentioned before, elements in the same family do have similar kinds of chemical properties. It affects not only what kinds of things they can react with, but in some ways how fast they react with those things. So before we get to the metals and nonmetals, let's go real quick to the table itself. Now, ordinarily, if we were in class, I would be handing you a periodic table right now, and we would kind of walk through and label some of these things. Next time we're in class, we'll take a minute and actually do this. But if you have a copy of the table somewhere, you might want to make sure that you jot some of these things down. So this black line on the periodic table, some tables have this line on it, some do not. This black line ultimately is what separates the metals from the nonmetals. On this side of the line, everything is a metal. On this side of the line, everything is a nonmetal. And then there are key elements in the middle that are what we call metalloids. And so mostly these metalloids kind of straddle that black line overall. So, there are 6 to 7 metalloids in particular. Even though aluminum is on that black line itself, we largely will consider aluminum to be metallic and have way more in the common with the metals than with the nonmetals, or even with the other metalloids. So what are some of the differences between them? Well, metals and nonmetals are kind of opposites in terms of what kinds of things they can do. So for example, a metal has the ability to conduct heat and electricity well, whereas a nonmetal does both of those things very poorly. So you can see those two are opposites of each other. Metals tend to melt and boil at high temperatures. Most of them, in fact, are solids. Nonmetals tend to melt and boil at low temperatures. Most of them are gases. So the ones that are solids melt at relatively low kinds of temperatures. So take, for example, sulfur. Sulfur is a solid at room temperature, but if you expose sulfur to just a little bit of heat, like in a burner flame or a lighter, that sulfur will melt almost instantaneously. And if left to heat long enough, it actually starts to vaporize, and the vapors are extremely flammable. So nonmetals tend to be very low melting solids in general, whereas metals tend to be very high melting solids. We have to raise them to considerably high temperatures to get them to melt. Metals contain high densities. Nonmetals do not. Nonmetals tend to be quite a bit less dense, especially the gases. Metals are usually malleable and ductile, meaning that we can hit a metal and instead of breaking, instead of shattering, that metal just gets into a thinner piece without breaking apart. Malleability is all about being able to hammer something into a thin sheet. So if you take a piece of metal and you just keep hitting it, eventually it will start to flatten out if the force is great enough. Ductility means that you can draw it into wires. So you're talking about something that has a lot of flexibility in it to be able to pull it into a long wire or hammer it into a thin sheet. Nonmetals that are solid tend to be quite brittle. Think about ice. Ice is not an element, it's a compound, but it's made up of entirely nonmetals. Water is made out of hydrogen and oxygen. Think about what happens if you hit an ice cube with a hammer. It doesn't spread out into a thin sheet of ice. It shatters. It breaks. Nonmetals tend to be very brittle when they are exposed to any kind of considerable pressure. There are some exceptions to that, but for the most part, that is largely their case. Metals tend to display a brilliant luster, meaning that they are very shiny. Nonmetals, on the other hand, tend not to be very shiny at all. So they do not present or possess luster. And at room temperature, we find that a lot of nonmetals are either solids or gases, whereas we find that no metal is gaseous at room temperature. Most metals are solid. Now, in both cases, we have one example of a liquid. Can anyone tell me the metallic element that is liquid at room temperature?
Isn't it mercury?
It is mercury. Mercury, element Hg, is a liquid at room temperature. It is the only metal that is a liquid at room temperature. Likewise, there is a liquid at room temperature for the nonmetals. Anybody know it? It's a little bit less known. That's okay. It's more of a trivia question than anything else. It's bromine. So that is one thing that they have in common. Bromine and mercury are both liquids at room temperature. They are the only examples in their category that hold such properties. Main difference, though, bromine very, very easily vaporizes and turns into a gas. Mercury has a much less significant vapor pressure and takes a lot more temperature to get it to boil. But you can see metals and nonmetals are opposite each other. The properties that are possessed by one of them are not possessed by the other, and vice versa. All right, let's close out today by looking at some common families of elements. Again, families, remember, families are the vertical columns on the periodic table. So let's start with group 1A. Group 1A, also known as group 1. This is called the alkali metal family. Now, the alkali metal family consists of lithium, sodium, potassium, rubidium, cesium, and francium. It is the first column over here. That first column of the periodic table. Now, notice hydrogen is in that column on the periodic table, but it is not considered an alkali metal. In part because it is non-metallic, it is a gas, and also because in part we don't know what it looks like when it's a solid. Solid phase hydrogen has not been achieved, at least not confidently, and we are unsure of what its properties are. It has been theorized that if we had solid phase hydrogen, that it actually would be metallic, and would have properties more similarly possessed by alkali metals. However, that much is largely unknown. What we do know is that elements in this family do react explosively with water and will ignite on exposure to air. These reactions with water will yield bases such as lithium hydroxide, sodium hydroxide, and so on. And that's one of the reasons why they are called alkali metals. Alkali is a shortened form of alkaline, alkaline meaning basic. So these are metals that will form bases in water. Our second group of interest, group 2A, sometimes better known as simply group 2. These are known as the alkaline earth metals. Now, as the name implies, these are basic metals as well. These will form bases when they react with water. The reason they are called alkaline earths is because most of these elements are derived from materials that we find in the Earth's crust. So beryllium, magnesium, calcium, strontium, barium, and radium, these are things that usually have reacted with oxygen, and we will find them in dirt, rocks, ores, etc. Now, comparatively speaking, these are not as reactive as the alkali metals are. You put a piece of calcium in water, it will react with the water, but is not going to produce nearly as much hydrogen nearly as quickly. It will form a base. The base will actually be insoluble in water for the most part. The reactions are considerably slower compared to their alkali metal counterparts. But they react in some kind of the same ways. If I heat them up and expose them to oxygen in the air, they will ignite, and they'll ignite pretty spectacularly. Magnesium fires are quite bright in their coloration. They are bright white light. Magnesium powder is actually often used in fireworks to help increase the brightness of the firework when it explodes. Calcium is often used for other kinds of firework effects for the same kinds of reasons. It gives off kind of a yellowish orange kind of color. So if you ever look at a firework being set off and that tail that's kind of going as it goes up into the sky, it allows you to kind of track it. That's usually as a result of calcium. On the flip side, group 6A, otherwise known as group 16, or I'm sorry, that's group 7A. I'm sorry, group 7A or group 17. This is known as the halogen family. The halogens, fluorine, chlorine, bromine, iodine, and astatine. This is kind of like the non-metallic version of the alkali metals. These are highly reactive non-metallic gases for the most part. And so these gases usually are quite reactive. They form a variety of compounds. They also form a variety of compounds with alkali and alkaline earth metals that make up the majority of salts that we see. So things like sodium chloride. You got the sodium from the alkali metals. You've got the chloride from the halogens. They come together, they make a common salt. And the reason for that is because you've got two peas in a pod, basically. You've got a metal that really, really wants to react and a non-metal that really, really wants to react. And you put those two together, and the reaction is usually quite violent and fast, but also very, very effective. The last family that we'll talk about today, group 18. These are the noble gases, and they are the last column of the periodic table. So over here, helium, argon, krypton, xenon, radon. These, generally speaking, lack reactivity, meaning they are unreactive, and those of them that are reactive are very, it takes a lot to get them to react. Usually it means that we have to get them in a tank with fluorine, which is the most reactive nonmetal. And the resulting product of that reaction is incredibly unstable. And so it very quickly wants to revert back to where it was. So on Wednesday, either in Zoom or in person, depending upon how the next 36 hours shake out, we will continue with this by talking about atomic structure and getting into some more general details about chemistry as an overall whole, and some more specifics about matter. Any questions? All right, I will see you on Wednesday one way or another. Have a good day. Stay warm.